Hello and welcome to Physical Chemistry tutorial number 3. Today we'll be talking about operators, eigenfunctions, and eigenvalues. So wave functions contain all information that can be known about a system. And for all observables, and these are quantities that you measure such as speed, linear momentum, there exists a corresponding operator that can be applied to the wave function. And eigenvalues of the wave function are the only possible values of the observable that you can measure. So for an operator, an eigenfunction is a function where if the operator is applied to the function, you will get the function back multiplied by a constant. So O in this equation is my operator, and I'm going to apply that operator to my wave function psi. So I'll write wave function. And if psi is an eigenfunction, I will get back a constant multiplied by psi. Okay? The constant I get back is called an eigenvalue. So in this case, it's k. So I'm going to write eigenvalue. So now let's get some practice with determining if a function is an eigenfunction of a certain operator. So in the first example, we'll have e to the 2x as our function with an operator of taking the first derivative with respect to x. So let's take the first derivative of our function with respect to x. Let's use u substitution. I'm going to let u equal 2x. So therefore du is going to equal 2. The derivative of 2x is simply 2. So I can rewrite this as d du e to the u. And the derivative of this is simply e to the u du, which in this case is equal to e to the 2x times 2, or 2e to the 2x. So now to determine if this is an eigenfunction, I set my result equal to my original function multiplied by k. If k turns out to be a constant, that means this is an eigenfunction, and k is our eigenvalue. So those two terms cancel out, and I get that k is equal to 2. So this is my eigenvalue, and since it's a constant, this function is an eigenfunction of our operator. So here we have another example. So now we're going to take the second derivative of cosine of x to the fourth. So that means I just have to take two derivatives. So let's break this down. Let's take the first derivative of our function. We'll let u equal x to the fourth, so du is equal to 1/4, and I can rewrite this as d du of cosine of u, and the derivative of cosine of u is negative sine of u du, so in this case it's negative 1/4 sine of x to the fourth. And so now let's take the second derivative of our function. Constants might flow out, so I can rewrite this as that, and let's use u substitution again. And so that's equal to sine of u. The derivative of sine of u is cosine of u du. So we have negative 1/16 du is equal to 1/4, and negative 1/4 times 1/4 is negative 1/16, and then cosine of u is cosine of x to the fourth. So if I set that equal to my original function multiplied by k, I get that k, these just cancel out, and I get that k is equal to negative 1 over 16. So that's a constant, so this is an eigenfunction with an eigenvalue of negative 1 over 16. And finally, we have f of x is equal to e to the negative 4x squared with an operator of taking the first derivative of this function. So if I take the first derivative of this function, let's use u substitution. U is equal to negative 4x squared. Du is going to be equal to negative 8x. So d du of e to the u. The derivative of this is e to the u times du. So I have e to the negative 4x squared multiplied by 8x, or 8x e to the negative 4x squared. So if I set this equal to my original function multiplied by k, I get that, if I cancel out these terms, k is equal to 8x. So this is not a constant because I have a variable x. So in this case, this is not an eigenfunction. Specifically, f of x equal e to the negative 4x squared of our operator. So let's talk about some important operators. The first one is the position operator in the x direction. We call this x hat, and this is basically equivalent to multiplying the function by x. So if I were to apply this to e to the x, for instance, I would just multiply e to the x times x. The momentum operator in the x direction consists of taking the partial derivative of the function with respect to x and multiplying the function by the complex number I, negative 1, and h bar, where h bar is Planck's constant over 2 pi. So if I were to apply this to e to the x, that would be this expression right here. The partial derivative is basically equivalent to the complete derivative because the only variable I have is x. The derivative of e to the x, the first derivative of e to the x is simply e to the x. So I have this expression, and then I would just multiply it by those numbers, and that's it. So the final operator we need to talk about is the Hamiltonian operator, and the eigenvalue you get back from applying this operator is actually the total energy of the system. So this operator is equivalent to negative h bar squared, where h bar is h over 2 pi, over 2m, where m is the mass, usually in kilograms, multiplied by the second partial derivative with respect to x, and we also add the total potential energy of the system. So V hat of x is equal to potential energy, which is usually given in joules. So all wave functions must be an eigenfunction of the Hamiltonian operator. So this actually leads to the famous Schrödinger equation, which is basically I apply the Hamiltonian to any wave function and I get energy back, which is my eigenvalue.